already stated before, so we're good to go. Now, we're going to talk about relativity of simultaneity. Suppose you have a moving train car at a velocity v full of passengers, and there's a bomb at the center of the train car. Bomb is configured in such a way that it'll detonate when it receives a simultaneous lightning strike at the front and the back of the train car. With respect to the train car, there's a stationary observer on a platform. At the exact moment that the bomb carrying train car intersects with the stationary observer, lightning strikes the front and back of the train with the stationary observer. Does the bomb detonate, or is there a temporal divergence due to link contraction and time dilation as a function of the square of the velocity of the train over c? And are the passengers saved? What say you, sir?
Well, I think we need to get a little bit closer on some of those definitions there. Like, because we need to think about it. I think the distinction is going to be whether there's a relative frame or an absolute frame, correct? Do you agree that if we assume a relative frame with a constant speed of light, then it would follow that simultaneity is relative?
What was your question?
If we assume a constant speed of light in all reference frames and the principle of relativity within those frames, it would be the case that simultaneity would have to occur in relative fashion. So my question to you is, doesn't your understanding of this example for us hinge on whether or not there exists an absolute lab frame on Earth, and where would it exist relative to that moving train?
Would the bomb detonate, yes or no?
Well, I think we need to define the terms a little bit better.
Answer the question.
So if
define the terms and answer the question. They're your terms to define. You're the relativist.
That's what we're trying to do. So our position is in accordance with relativity, right? So
what does relativity say?
I have the answer on the screen, if I may, Sea Lion. Yeah, what is shown here, and there's a GIF, so bear with me because it's animated, but that's a good thing. From a position, let's say A and B denote three independent events, three bombs exploding. From the point of view of a stationary observer, V0, all three happen at the same time. You can see it right now. All of them are happening at the same time. An observer who's moving with a speed 0.3 sees, wait for it, C occur first, then B, then A. And this observer, the opposite. This is
so
what
your argument is that the train would not blow up due to the velocity of the train.
I couldn't follow your description because you were speaking so fast that you lost me after the first two sentences.
Do it again.
Do you have a picture? Can you provide some kind of picture that you can walk us through
the point
step by
is,
step, like the way I walked you through the muon measurement?
Go to Google and type relativity train car.
No, I'm not going to Google. Okay. I want you to walk us through it.
Got you.
The point is, no amount of relativity makes that bomb not explode. That's the correct answer.
Yeah, that's
as you can see, all three events occur.
No matter where you're looking at it from, it goes boom, Peter. No matter where you're looking at it from, doesn't matter.
That is true. That is true.
Okay, so then there is an absolute frame.
No, all events occur. The three independent events, A, B, and C, occur in all frames of reference.
Then there's an absolute lab frame then.
No, clearly there isn't. The coordinates for the moving observer are rotated through the ether.
So your argument is that that the bomb wouldn't detonate because of the velocity of the train.
Again, you have to walk me through your thought experiment step by step because your speech was incomprehensible to me.
Okay, well you can go back and listen to it then on the playback. Here we're going to read.
I shall do that.
Here we're going to read back from the definition of simultaneity here, where he says. And then down at the bottom, we shall not here discuss the inexactitude which lurks in the concept of simultaneity for two events at approximately the same location, which can only be removed by abstraction, which is what you're doing right now, because we all know the train would blow up, and which implies that there's an absolute frame for them all to be relative to. And the hypothesis of the ether theory is that all events will occur simultaneously in the ether. Guess where the ether is at? In the lab frame on Earth. Now. For the next part, you were saying.
Hold up a second. Let's pull it out a little bit. So,
what's up?
You say that the
no.
This within an absolute frame.
But before we move on, both of you guys.
That's important because you just slipped that in there. We need to. That's a very important point, though. We need to address that.
Okay, just write it down. Remember that. Go ahead.
Before we move on, Both of you guys agree that the train blows up in all frames and the velocity of the train will not save anyone.
I don't, because I couldn't follow your experiment, your description of the thought experiment. You were speaking too fast.
Okay, how about Sea Lion Prime?
I concur with Peter.
You concur with Peter?
God.
All right, bro. We're gonna run it one last time.
Yeah,
Walk us through it. Can you show us a picture? It's very hard to visualize these things purely based on speech.
Well, keep trying to stare at your picture and just think real hard that it won't explode. That's what you could.
Yeah.
That wouldn't be intellectually honest on my account.
It'll be perfectly honest.
Can you stop that share for me, Peter? Thanks.
Suppose you have a moving train car at some velocity full of passengers and there's a bomb at the center of the train car. The bomb is configured in such a way that it detonates if it receives simultaneous lightning strikes at the front and back, similar to the the standard example that they give for the moving train car and the stationary observer at the center. Right? With respect to the train, there's a stationary observer on a platform. At the exact moment the bomb-carrying train intersects with the stationary observer, lightning strikes the front and back of the train car. Okay? Does the bomb detonate, or is there a temporal divergence due to the velocity of the train?
Yes. I am familiar with that. It's a common, puzzle in relativity. And the solution is well known. I don't remember it.
That's a real shame. Sea Lion, you.
So what would this apply? So let's think about this for a second, because
it's impossible to solve it. It's impossible to solve it this way. You have to draw geometrically all the relationships, and it's actually given to students in universities to solve this particular conundrum. There's a very well-known solution. This is a debate tactic to throw at you something that it's complex, that has to be drawn and calculated using angles and lengths, and now it's presented in a verbal form, and it's impossible to explain it correctly unless you just did it on a piece of paper and just are reading off your notes. So this is a trap.
Didn't we make up the train bomb example, dude?
It's a basic question, and it even says here in Einstein's 1905 paper, we shall not here to discuss the inexactitude that lurks with the concept of simultaneity for two events at approximately the same place, which can only be removed by abstraction. Right?
So it's hard to think about these things because they're counterintuitive.
No, you guys all agreed that at one point that the bomb would go off, and then you stopped when you realized the implication of an absolute frame.
You're on the lab frame, right?
And then now you're appealing to an equation that doesn't exist. And I'm not even going to pick on you and tell you to. And I'm not even going to pick on you and tell you to pull it up and show me right now. So I don't give a shit. I know the bomb blows up and
they're spiraling. So in special relativity, there's no such thing as violation of causality. And there's no such thing as events occurring or not occurring depending on the observer. This is very well known. And all the paradoxes in relativity that are given as thought experiments for people to calculate and compute, that is done every day in every university on Earth, have a known solution within the special relativity.
What's the solution for the muon paradox?
Gotcha. Okay.
I just provided it to you.
Yeah, we just talked about it. So
let me ask you this: Would you board the train then? Would you be on the bomb train and take the risk? No.
No, not without having first thought through the thought experiment. I would sit down for a few hours. I would think through the thought experiment. I would employ the services of a person who's familiar with these problems to help with my poor knowledge of geometry, and I would then answer your question.
Let me ask
would you get on the train?
Let me ask you about the implications of that question, though, because you mentioned
the implications are you die. Would you get on the train or not?
There's two things that are related to that question that get back to this idea of the absolute frame. So thus far in the debate, we have not established a constructive difference between a theory of the ether and a theory of the relativity on the basis of what we established of our definition of ether. The only thing that will distinguish them on the basis of what we've talked about so far is the existence of an absolute frame. Now, there's two components that we need to talk about with relation to this supposed absolute frame. The first one is we've identified that unless you have another piece of evidence you want to discuss, your only piece of evidence for a one-way speed of light calculated within this absolute frame of reference was from GPS. which by itself would require calculations and adjustments by your own admittance. So I don't see how that's compatible with an absolute model of an absolute frame. But the other question I have for you is, you mentioned that the ether is within that frame. Can you expand on that piece specifically? You said the ether is within the absolute frame.
Yes.
Okay.
There's a translation of motion that comes from the sky that follows sidereal time. This is measured with interferometry. As you increase in altitude, you measure a faster velocity, right? So in the same, what according to what? What do you mean?
What experiment? What experiment has measured that?
Oh, Yuri Galev, Dayton Miller, and Picard.
Yeah, but I already provided you.
I
provided you with an alternative explanation for the Dayton Miller experiment.
Oh, yeah. So your alternative explanation is invalid. The Sagnac effect has no relativistic derivation.
That's a completely false statement. Would you like me to provide you? Would you like me to provide you with multiple statements to show that that's an incorrect statement?
Yes.
Okay, great. So let me go ahead. I have some sources right here. Let me pull that up for you. So there's the original derivation, and then there is, so you're familiar with the history of the Sagnac effect and its interpretation in relativity, right?
Are you sharing? We don't see anything.
I'm about to share now.
Okay.
Sorry.
Who is Yuri Galev?
Dude with an interferometer.
So here's a paper right here. The Sagnac effect and its interpretation by Paul Langevin. Langevin, sorry.
Yes.
Okay, so what is your criticism of the derivation in this paper?
Let's see. So relativity theory doesn't predict a fringe. That's my criticism. You can't hold on one second. Yes, yeah. You can't predict a fringe pattern without invoking a preferred frame at the center of the device. Relativity theory.
Show that to be the case with any sort of paper or result. How are you measuring that? What do you define as a fringe?
That's how Paul Langevin derived it, right? You invoke a geometrically convenient position at the center of the device for the motion to be relative to.
In the derivation, walk me through where that happens. Because that's an affirmative claim. Now you're saying that this is an invalid representation of the phenomena, and I can pull up a large number, if my computer will cooperate with me. I have a large number of papers here.
So large number.
Yeah, I mean, I'm learning from the best. You guys have good papers, so I got to keep up. You know what I mean?
Dude, how come every question is you ask us 6 more questions and don't answer any of our questions? How come we have to answer all your scattergun bullshit?
It's fine. Because you're making a strong affirmative claim on this absolute reference frame, and thus far.
So listen. I got you. Here we go. So this is the Dufour and Prunet Sagnac experiment that they did, right?
Yeah. Let's take a look.
This is this is their configuration they had here. Okay.
Oh, you're showing your screen. Sorry.
Yeah, I'm going to explain it should be sharing, right? Okay. Now, here's Paul Langevin trying to explain it through using general relativity. Right?
I don't see it. I just see you scroll some stuff on,
Yeah, I got to stop my screen share, I think.
Yeah, watch my web.
You already have it. Yeah, okay.
We can do that too.
Okay, so this is their apparatus. They had
I cannot resolve anything in that small thing. You need to show it.
Click on it.
Click on it and make me the center.
Yeah, I put it on the screen.
Well, it's still just.
I'm just curious. Okay, so let's talk through this. So
okay, let me talk for a second then, instead of you half talking for me. Okay, so the Sagnac effect here, right? They had this experiment where they have a rotating table and they have a stationary table on top of it. They're using angled 45-degree mirrors and a source that's stuck to the wall on the lab, and a detector that's stuck to the wall on the lab. The source emits light, hits the prisms, gets split through the beams, and then it hits the rotating frame, and then it ends up back at the wall in the lab, right? Now, relativity tried to explain this experiment, specifically Paul Langevin, and he comes in to say,
did you know you can call AI now?
I can call it and talk to it?
You can call it and talk to it, and it's free.
So I can ask it anything and have a real conversation with it like a real person?
After making the wrong prediction, right, he says, the relativistic theory thus seems to be in complete dissension with the classical theory and also with the results provided by experiment. But given that Paul Langevin appeared to allow the value to be reportedly higher, we considered that the center where the theoretical relativist must be presumably placed at the must be arbitrarily selected. And the relativistic theory found this contrary to the agreement with the classical experiment. This experiment, if the center is obligatory collinear with the center axis of rotation of the disk, this only point on the disk, which it can be a permanent origin of Galilean axis, not subjected to rotational moment. This is despite the explanation Mr. Langevin said to us when he arrived after being informed of the results of our experiment. So Paul Langevin was saying that he could derive this, no problem as a relativistic effect, and he could only do it invoking a preferred frame at the central axis. When you set up for a Lorentz transformation, here we go with, let's see, what was his name? Tartaglia. Tartaglia does the exact same thing to try and address the Sagnac effect. There is no frame that predicts the amount of fringes in relativity theory unless you invoke a preferred frame. One second, where's mine? What am I looking for? Tartaglia. 1 second. Here we go, Tartaglia. So what they do is they set up for a geometrically convenient position here, right? Oops, the frame's a little messed up, or the picture's a little oversized, but you guys get the gist of it. The world line is noted here in the center axis of the rotating device for the fictitious frame, and then the deviation here is the rotation for an observer at the rim of the device. This is how the relativist explains the Sagnac effect, right? By invoking a geometrically convenient position, always. This can't be answered with the Sagnac equation, or like it can be with the Sagnac equation. You have to invoke a preferred frame. Now, when you get into the derivations for the Sagnac effect as a relativist, you will find, nope. We're getting close. You feel it?
I do.
All right, 1 second. Right here.
Here's
so here's relativity, right? Assuming a constancy of the speed of light for the two observers, right? So we have a source and a recorder on a platform that's rotating, right? You agree? The Sagnac effect, classic Sagnac apparatus setup, observer recorder on a platform that's rotating. Okay, uniformly rotating. Relativity predicts that they're an inertial frame, so C will be measured as C for both of those people, right? So if you math that out, what you're going to get is C going clockwise and C going counterclockwise will be the same speed, which will produce no fringe shift pattern. There's no way to explain this without invoking the geometrically convenient position and doing a Lorentz transformation. That was shown by Tartaglia here.
Sorry, go ahead. My bad.
Sorry. This was shown by Tartaglia here, where you can only explain the Sagnac through geometrically convenient positions. Now earlier we were talking about Michelson, Gale, Pearson, and whatnot, right? So we have.
Hold on. Let's before we go there though. Before we go there, I think there's important. What do you mean by geometrically convenient?
At the center of the device where it's stationary and non-rotating.
Okay, but what is the issue with that?
It's a preferred frame, and relativity can't derive a solution without invoking it, because relativity predicts that. So let's assume that link contraction and time dilation would apply to the apparatus. The fringe shift pattern that relativity would predict would be much smaller than the one that's measured, right? Because the velocity is a one-to-one relationship, whereas relativity predicts that the fringe shift would be the square of the velocity over c squared, which would be much smaller than what's predicted.
Can you show that? Can you show that derivation specifically?
Yeah, that's link contraction and time dilation, right? Okay. That's the square of the function of the velocity.
So what's the discrepancy?
Yeah. So I'm still not understanding how this creates a preferred frame.
The discrepancy is relativity predicts a much smaller fringe, and it can't do it.
Right? It can't do it.
Can't.
But that's just a statement you're making.
No, it's actually shown here in Tartaglia's paper with the geometrically convenient position that he had to invoke to try and explain it. And then he had to do the same thing for Ruyang Wang's experiment, right? He had to invoke a geometrically convenient position in the center of that as well. Like you guys want to see some geometrically convenient positions real quick? Check this out.
Not necessarily.
Linearize it, generalize it.
Where's our boy? So this is Barada, 2022, trying to explain the Ruyang Wang and the Sagnac effect as a relativist. And here we're going to look at, he's going through a thought experiment. He's breaking it down, realizes that even with the gamma factor, there's no ability to explain it. And he goes on to say,
Working 40 to 50 hours per week is robbing you of one thing that you can never get back.
Though mathematically it is fine, but the physical understanding of the effect from the standpoint of an observer attending the rotation remains difficult. Why is that? Because relativity predicts no fringe shift pattern. We have Post in, what was it? Post in, what was it, 1967? Right, we're going to read a comment from Post. 1967, to be consistent with the principles of relativity, one has to demand that the Sagnac interferometer ring laser cannot lead to a fringe shift or a beat frequency if the equipment is in uniform translational motion. And then obviously this is a direct contradiction. Now, Einstein says that his equations apply in a curve where it's uniformly, or any polygonal circuit that's in uniform rotation. So if you continuously do a curve, that's a circle, and if it's in uniform translatory rotation motion, then his equations should apply, and the fringe shift pattern would either be no fringe shift pattern, or it would be much less than the velocity of the fringe shift pattern. Because
when is the latest paper that you're citing on this topic as it relates?
2022.
Okay, perfect. So I have here another paper that seems to contradict what you're saying, and I'm not understanding the source of the contradiction. So this paper presents a relativistic explanation based purely on special relativity that describes the fringe shift that you're talking about. So is this then required? So there are two things tied up in this. I think you said that there's a preferred reference frame set by a geometrically convenient position. But I also know of another paper where they have a sort of more general approach to the Sagnac effect, where there's basically a difference in the way that the loop is centered, and they're still able to define the effect relativistically. So I'm not sure that is required for this.
It's absolutely required. I'm sorry.
Well, why is it required?
If the speed of light is constant and you're in uniform motion, you measure C as C, and you measure it because of link contraction and time dilation in the moving frame. So if you're in uniform transitory motion, relativity predicts that C will be C, and if C is C, then it's going to complete the circuit at the speed, and there's going to be no fringe shift pattern. It's going to combine at the same time, but there's not.
This paper is directly contradicting what you're saying. So, I mean, obviously, I'm putting you on the spot to speculate on this. We could read this paper more in detail at a later time. I just don't know that this is an accurate statement of how special relativity approaches this problem. And then kind of going back to this, the implication of this would be what? A non-constant speed of light in an absolute reference frame or a preferred reference frame? What would be the implication of what you're saying about the Sagnac effect? Because I dispute on just the papers that I've read, and I'm citing one in particular right here, that what you're saying is not correct.
The implication is that all velocity is measured with respect to the ether.
Okay, and the ether, you said, is within your absolute lab frame.
Yep.
Ooh. So, okay, let's dig into that. But there's also an ether wind.
Well, let's stick with the Sagnac and the derivation.
Yeah. But I'm trying to understand the Sagnac effect in relation to the ether, because that's the distinction.
You're explaining it with the rotation, right? That's what this paper is saying, and that you're ignoring the linearization and generalization aspect of it completely. Is that where we're at?
No, and that's not what I'm saying. So when it comes to the Ruoying Yang and the linearization, that's an attempt to apply a different interpretation. But I can also show you a paper that suggests it's an attempt to apply a different interpretation to the Sagnac effect, one that has never been empirically demonstrated.
He did it 3 times. Did it 3 times.
So let's. I have a direct paper that speaks to. I have it right here. I have a paper that speaks to specifically the issues. This is.
It's not a rotational effect, so using a rotational frame to describe it is kind of silly, right? Is that your argument?
It is a rotational effect, as a matter.
Of course not. That's what Ruoying Wang proved in 2001.
He didn't actually prove it. So when you look at the actual derivation here, and this is also kind of strange because you seem to have imposed this arbitrary standard on us that we can't use certain forms of mathematics. But now what you're saying is, well, this person did a certain transformation and seemed to suggest that rotation could become linear. And what I'm telling you is that this paper right here, which I have a copy of, I can certainly send to you, And this is from Spavieri et al. It basically goes through, and I have the DOI. I can send you the citation. It essentially shows that Ruoyang Wang essentially was just basically doing what you accused us of, which was some sort of mathematical trickery. And that's supported by the fact, no, that is correct. And it's supported by the fact that there's never been would you agree that there has never been demonstrated a device based on the linear Sagnac effect to measure linear motion in that way?
He has a patent for it, doesn't he, Alan? But anyway, that's not
what I asked you. That's not what I asked you. There's plenty of patents out there that don't lead to.
You said that it's not a rotational effect. It absolutely is, and it was linearized, meaning that the travel time difference is proportional to the area enclosed by the path of the angular velocity of the rotation, right? Well, hold on, dude. Right, hold on. You've been talking an awful lot, right? What are you getting scared for? It's all right. So, like, when you're saying that it's not a rotational effect, and then we're saying that it actually is observed in a linear system.
Can you mute your mic while
Just
he's
wait.
talking?
Yeah, just mute it, please.
Sorry, my.
We're saying that it is observed in a linear system. That's what Ruoyang Wang proved with his paper. That's what the mathematical formula is derived from, right? It can be, by the fact that it can be derived, negates your position. By assuming that light travels in relation to a fixed laboratory frame, that is the whole point. Without that, they wouldn't be able to do this. This is, in fact, the direct contradiction to your supposed paper explaining the Sagnac effect with yet another rotational system. What do you think, Alan?
Here's the problem, though. Here's the problem with that, because I can provide another paper which specifically critiques the methodology of Wang and proves that all he did was reset the coordinate system in a way that made it look linear. And that's supported empirically by the fact that there has been no device ever produced. Notwithstanding. Right. Do you understand how revolutionary this technology would be if what you're saying is true?
What was the shape of his interferometer?
Hey, Sheila,
right here.
What did it look like?
We're still within our time, right?
Come on, Peter. What did it look like?
You both have about 15 minutes left.
Okay. I have an idea how to get us out of this conversation. I'm worried that the audience might be asleep at this point.